Okay, now we're back for page 250, number 6. Number 6. This one is a pedigree question. So what I'm going to do is I'm going to copy the pedigree out here. We have remember the symbols, right? So here's our female and there's our male. And then they have these children. And the children look like this. And then this person has a mating. This female mates with this male and produces something like this. Now, we need some colors here. In the book, they have shading. I can't do shading. So I'm going to use black and color in black for the ones that are showing the sickle cell anemia phenotype. They actually have sickle cell anemia. That's this one and this one right here. Okay. Now, if you go back in your book, you'll notice that sickle cell anemia is on page 244, and it is an example being used of a codominant situation where both are expressed. So you get both. You get both regular cells and sickle cells if you have... well, let me just go down here and remind you what that means. What it means is, and if we use the textbooks, what they do is, I'm going to just put an H. They put a little HB for the hemoglobin molecule, but just use an H. It doesn't matter. You can use a Z or a P or whatever you want. But the main thing is that you have what's called a normal, which I think they use for, they use a little A. This is the normal allele. And then they use an S, so we'll just use S for the sickle cell allele. And so remember that this gives you normal. If you have this cross, your phenotype is normal. If you have double S's, you obviously must have sickle cell anemia. You're sick with this disease. But if you get this, the heterozygous, what it means is that you express both. So you have both normal and sickle cells. And remember what we said about that. When you have that, you don't really notice that you're sick. The phenotype is pretty much, you're still fairly normal. The only difference is that the few sickle cells that you do have actually make you more resistant to malaria, right? So this is the dark circle that I just colored in, sickle cell anemia. And these would be the open white circles or squares. And then the last one, I'm going to have to use a different color because I can't really do shading here. So I'll use a red color for the ones that are just sort of shaded in. And on back on 250, then we have this one shaded in. So that's a half and half carrier, right? And then this one is shaded in, carrier. Okay, so it says to determine the genotype of these individuals on this pedigree. And so we already know some of them because we know that if you were the black colored in dot, you had to be sick. So you have to have genotypes where you have homozygous sickle cell carrier. I'm not sure why that's not writing an S. There we go. So we know those two guys. They're done. We have their genotypes. We also know the red ones because remember, if you're a carrier, that means you have one normal and one sickle cell. So that's this one and the same for this guy over here, or this girl, I should say. Now we have to try to figure out the others. And we have to do that by looking at different possible crosses. So let's look at, first of all, let's look at the situation here on this side. And let's work on this square and see if we can't figure out what it would be. Well, we have to imagine a cross. We know one parent is HA and HS. That's the red circle. We're crossing that with an unknown parent, but we also know that we're getting at least one of the possibilities is this offspring. Now, that doesn't mean they all have to be that, but at least that has to show up in our cross. So what we can do is we realize that there's two ways we can get that to happen. Right? There's two ways we can get that to happen. One of them is if we cross with a carrier, right? As long as both parents have the HS in them, right there and right there, it's possible when you do the Punnett square that those could match up and produce this sick individual down here. But if the parent had this, guess what? They'd be a carrier and they would have been colored red. And they're not colored red. So we can actually figure out that, or we can basically deduce. Oh, I see the problem. We can't. The question says on the side that they have a normal phenotype, but they're not tested. So even though they're not colored in, the truth is they could be white or they could be red. All right, so that makes it a little tougher. That means we have to do both crosses. So let's go back to what I was talking about here. I'm going to slide down. What we have to do is we have to do a cross of HS. And remember, we had one who was a carrier. So let me make that HA. Scratch that out. We need to do a cross of an HA, HS. That was the red, or the shaded in, number 3, if you're looking at the textbook. It's the number 3. All right? And then we're going to cross that with someone who might be a carrier. Okay. What are the possible gametes? Well, this parent can produce this gamete or this gamete. And this parent can produce the same, that gamete or this gamete. So if we do the square, we have to do both gametes this time that the parents can make. There's one parent, and here's the other parent. And then you see what we get. We get HA in this box. We get HA, whoops, that's an H, not an A. HS in this box. And then we get HS in this box. And then we get the HS down here. And that's the sick person. So it's possible to get this sick person if we use two heterozygous individuals. So that square that I'm pointing to here, that could be this, HAHS. Okay, S. Well, come on. Doesn't want to work for me now. There, HS. But the other possibility for that is that it could be the carrier, HAHS, but maybe that individual is normal. We don't know. Maybe they're completely normal. Right? So if they were completely normal, because you see that it's a white square, then this is the cross. And if we did this cross, we could see that there would be this gamete and this gamete, and we would cross it with only one possible gamete on this side. So guess what? Our square now looks like this. And we get HA here and HAHS here. What this means is it's completely impossible to get this genotype. It doesn't exist. There's only the heterozygous or homozygous normal. So that parent can't be normal because they have a child right here who is sick. Then it's impossible to get a sick child if one of the parents is completely normal. So that means we've confirmed that our first guess is right. This up here is the genotype for this guy right here. Done. HAHS. It has to be heterozygous. That's the only way we can get a sick individual. Now, when we look at the next part, I'll go in yellow over here. Whoops, all of this sort of family. Well, we have a problem. We don't know either one. Right? We know that one is sick and we have 2 carriers. So that means there's a very good chance that these recessive alleles are in there somewhere. They have to be. So again, what we could do now is look at the 2 possible crosses. Now we've already done the crosses, right? If we had, we've done some of them. Let's look at this cross. We've already done the cross of 2 carriers. And we see that it's possible to get normal, carrier, carrier, sick. So that cross could describe those 2 parents because their children, we have sick, carrier, carrier. So that could be it. But we can't say that's the only answer because we have to also look at this cross. This cross would not work, right? First of all, no one gets sick in this cross. There's no way for sick. So this second cross of having HAHS and HAHA does not work. And of course, we can obviously see that this cross would not work. If both of those parents were completely normal, there would be no way you could get any sick individuals. So that cross doesn't work. So the only other cross that we haven't done, there's 2 of them, that would be a normal individual, HA, crossed with a completely sick individual. So let's do that square and see what we get. In that case, we have 1 allele here and 1 allele here, which means 1 gamete, right? So when we do our cross, it's very simple. And all we get are this, carriers. No sick. Again, none of these sick individuals exist in that cross. That means if we go back here, look, this one right here is sick. So that cannot be the case. So far what we've found is that this one can work when they're both heterozygous. This one does not work. That's 1 normal, 1 heterozygous. Both normal doesn't work. What about if they're both sick? That's the only one that we haven't tried. Well, if they're both sick, right? Then here's what you get. HS crossing with HS, which means everybody gets sick all the time. There's only 2 alleles. And of course, look at their children. They're not all sick. So watch what I'll do. I'll summarize because we've been jumping around a lot. I'll summarize what we've done there. We've done all the possible crosses. We said normal parent crossed with normal parent. And when we did that cross, we got only normal results. Only normal. So we said that one does not work because obviously the children were carriers and sick. Then we said, let's do the cross of normal with a carrier. And when we did that cross, normal with a carrier, right here, this was the normal, right? If you look on this side, normal, carrier. We saw that the children were always going to either be normal or carriers, and there was no way to get a sick child. There is none of this genotype. So that didn't work. So in other words, the only 2 options there for phenotypes are normal or carrier. So that one doesn't work, right? And then we did the cross of this one, which was 2 that were sick. So had homozygous sick, right? HS crossed with HS. And we found that all sick. All had the disease. No carriers. So that can't be the answer because we obviously have 1 sick child and 2 carriers. So our last cross that we did up here, this one, was when you had 2 that were heterozygous. And when we did that cross, here it is, we see that you can get normal, but you can also get carriers and you can also get sick. Right? Now, what do we have for our 3 kids? We have 2 carriers and a sick, which means we need this and this. And this is the only cross that gives us those 2 combinations. So we can determine by process of elimination that this is the only cross that will work. So what that means is if we go back, this gives us both carrier and sick. And it also gives us a chance for normal. And here's the funny thing. You got to remember, these are squares that give us probabilities. You don't have to have them all. You just have to have the possibility of having them. So the fact that this person had no normal children, this couple, doesn't mean this can't work. As long as the children they had fit this, then it works. So this is our answer. So I'm going to take red here. I'm going to say, nope, this one did not work. This one did not work, and this one did not work. If we look at it, only normal can't have the kids we had in the pedigree. Normal or carrier, we can't have a sick child. All sick, we had carriers. This is the only one that works. So now we know that the genotype of those 2 people up here are HAHS. They have to be both carriers in order for that to happen. So we've answered the question. There are none that we cannot be certain of in this case. Now we have to do a little cross. They want to know what will happen and what the probabilities will be in part B if we take this person. I'm running out of colors. Maybe I'll pick this purpley color. Okay. And so I'm going to take person 2nd generation 3. So that's this person right here. And they want to cross them with another person who is 2 and 4. So this person, they want to know what are the chances that they will have another child with sickle cell anemia. See, they already have 1 down here. So all we have to do is cross their 2 genotypes, which were this one, HAHS, and this one down here, which is hiding there. But remember, because it's a carrier, it has to be this. So we're going to cross that with this one up here. Okay? 2 carriers are going to be crossed. Well, we've already done the cross of 2 carriers. We can go back to 2 carriers would be 2 heterozygous crosses. I guess it's this one right here. Here is the cross of 2 carriers. See? Carriers, 1 of each. And when we did it, we saw that we had 1 out of 4 normal. That's this one right here, 2 HAs. We had 1 out of 4 sick with sickle cell anemia. That's this one with the 2 S's. And we had 2 out of 4 who were carriers. They have 1 of each. Carrier. So what is the chance of them having another child who is sick with sickle cell anemia? 1 out of 4. Whoops, sorry about that. How do I go back to where I was? I guess done. Nope. Now I can't find where I was. Hang on a second. I will find it. Here we go. There we are. So, what are the chances? 2 out of 4 of having a child. Oh, wait, sorry. A child who is sick. 1 out of 4. 1 out of 4. This child right here. 1 out of 4. So the answer to part B is simply 1 out of 4. Now, if you were doing this as a question, you should probably do the cross again, right? And we said they were both carriers. So HAHS. These are the alleles. And you do the cross, HAHS. Good practice anyway, right? Doing the crosses. And HSHS. Okay. And then you could write down the genotypes. So for HA, which is a normal person, 1 out of 4. And for HAHS, which is a carrier, 2 out of 4. That's a 4. And for HSHS, which is someone who is sick with sickle cell anemia, 1 out of 4, or 0.25, right? Those are the chances. So that's how you do the pedigrees. It's kind of like detective work, where you have to sort of try to figure out what you can determine right off the bat, like we did, by seeing who's sick and who isn't. You also have to remember that sickle cell anemia is a sort of codominant type situation. And that's why you have to also remember that to check back in your textbook sometimes. All right, and you play this detective game and you do all the different crosses and you just see what the possibilities are for the children that they have. Okay, good, we're done with that one. Let me see here.